All right, let's look at the questions for section 3.2. So now that we've seen how to find eigenvalues and eigenvectors, we can use that information to solve these systems of first order differential equations that are totally coupled, as long as they're linear and homogeneous. So here's essentially what we're solving. We're solving a matrix equation now where I have dx dt, where x is a vector made up of x prime and y prime. That's equal to the matrix A times the vector x. So dx dt is a 2x1 column vector. X is a 2x1 column vector. And A is a square 2x2 matrix. So essentially what we're asking, we know what dx dt is. We know what A looks like. We would like to find what X is. So the way to do that is to find the eigenvalues of A. A is going to be populated with all the coefficients of X and Y. So -3, 4, 3, -2. And how do you find the eigenvalues of A? That comes from solving this equation. So the determinant of A minus lambda I, and set that equal to 0. So -3 minus lambda times -2 minus lambda minus 12 equals 0. 6 plus 2 lambda plus 3 lambda plus lambda squared minus 12 equals 0. Lambda squared plus 5 lambda minus 6 equals 0. All right. How does this factor? This should factor down to lambda plus 1. Nope. Lambda minus 1. Lambda plus 6 equals 0, which means I have eigenvalues of -6 and 1. Great. So from there, I need to find an eigenvector that goes with each of those eigenvalues. So what is A minus -6i? So A plus 6i looks like this. -3 plus 6 is 3, so 3, 4. -2 plus 6 is 4. So I get this matrix here, 3, 4, 3, 4. So what does either row of this tell me? Basically 3x plus 4y equals 0, or 4y equals -3x. So let's find a vector that captures that relationship. Let's say x is 4. If x is 4, then y has to be -3. And I'll remind you, eigenvectors are not unique. You could have an infinite number of vectors that are correct that don't look like this. For example, -4, 3 is a good one. 1, -3/4 is a good one. As long as that ratio is respected, you're fine. Now, what does A minus I look like? That'll be -4, 4. So basically, and to be clear, the way I'm making these new matrices is, since these are alpha A minus lambda I, I'm basically subtracting whatever my eigenvalue is from this major diagonal. So from top left to bottom right. So -3 minus 1 is -4. -2 minus 1 is going to be -3. The entries that are not along that diagonal don't get altered. So here I have another linearly dependent matrix. So -4x plus 4y equals 0. That implies that y equals x. So any vector where those coordinates are equal is fine. So now I have an eigenvector that corresponds to lambda equals -6, and an eigenvector that corresponds to lambda equals 1. So what does that mean about my solutions? So x of t is going to be equal to 4c1. So, and to be clear here, each one of these vectors, these eigenvectors, the top row of each one represents something about our solution in x. The bottom row of each one represents something about our solution in y. So 4c1 e to the -6 t, because that's our eigenvalue. Plus 1 c2 e to the t. So a lot of ones there. The eigenvalue is 1. The x-coordinate of the eigenvector is 1. All right, so that's what we have for x. What about for y? Y of t equals, now we're going to look at the bottom row. -3 c1 e to the -6t. And bottom row of the other vector is also 1, so plus c2 e to the t. All right, so that is our solution for our first system. All right, let's move on to our next question. Number 8. So now we're finding particular solutions. We have initial conditions now. But the way we find the general solutions is going to be essentially the same. We need to find the eigenvalues of this square matrix. 6, 4, -8, -6. And I need to put my eigenvalues or my lambda in there. 6 minus lambda 4, -8, -6 minus lambda. So what is the determinant of this? That's equal to 6 minus lambda times -6 minus lambda minus -32 equals 0. So -36 plus 6 lambda minus 6 lambda. We like that. Plus lambda squared plus 32 equals 0. That cancels, so I get lambda squared equals, or -4 equals 0, which means that lambda equals plus or minus 2. Okay, now I need eigenvectors that fit either one of those. So now I want a minus 2i. That will give me 4, 4, -8, -8. So either row is fine. 4x plus 4y equals 0. That implies that y and x are same magnitude, different signs. So good eigenvector there is 1, -1. What about a plus 2i? That'll be 8, 4. And -8, -4. All right, that implies that 8x plus 4y equals 0, or y equals -2x. So now a good vector will be 1, -2. So from here I can write my general solution. X of t is equal to 1 times c1 e to the So let's be clear, what was my lambda value here? Lambda equals 2. Lambda equals -2 e to the 2t. Plus 1 times c2 e to the -2t. And then y of t will equal, now we're going to look at the bottom row here, negative c1 e to the 2t minus 2c2 e to the -2t. So that's a good general solution, but how do I get my values for C1 and C2? Now I'm going to figure out what happens when I plug in my initial conditions. So x of 0 equals C1 plus C2, and I'm told that equals 1. Y naught is equal to negative C1 minus 2C2, and that's equal to 3. I can go ahead and add these equations straight down. And if I do that, I get negative C2 equals 4. So C2 equals -4, which means that C1 equals 5. All right, so what's my final system here? X of t equals 5 e to the 2t minus 4 e to the -2t. And y of t equals -5 e to the 2t minus 2 times -4, so plus 8 e to the -2t. All right, so there's my solution set for x and y. And moving on to 11. So now we have a parameter in a system. For what values of a do you find a bifurcation? So let's find that bifurcation value. So how do we do that? I'm still looking at solutions for x and y. So I need to set up my A minus lambda I matrix. A minus lambda 1, 2A, 2 minus lambda. So here's my characteristic polynomial, A minus lambda times 2 minus lambda minus 2A times 1 equals 0. Expand everything, I get 2A minus 2 lambda minus A lambda plus lambda squared minus 2A equals 0. So lambda squared plus lambda times what? What can I factor a lambda out of? Minus 2 minus A. And then my constants cancel out. Okay, so that's going to make this a little easier to solve. So what are my eigenvalues now? I can factor out a lambda. And the other part becomes lambda minus 2 minus A equals 0. So what are my eigenvalues? One of them is definitely 0. The other one is A plus 2. So where am I going to have where am I going to have a difference in my phase portrait? So one thing we've seen in this section is we know what this looks like. Basically, everything we've talked about so far is when our eigenvalues are real and distinct. So what's going to cause that to be different? The only thing that's going to cause that to be different is where A is equal to -2. Under the condition A equals -2, we're going to have eigenvalues which they're the same. We have two eigenvalues which are coincident. Without getting into what the phase portraits look like, that is going to suffice to say those are going to be different. We'll talk in the next section about what specifically those differences are.